So here's the observations of one of these examples where you can see the data is normal 0, 1. But on this side, we have these two quote-unquote mistakes, these two outliers. And these two outliers make the p-value be 0.05. If we take those two outliers out, the p-value is no longer 0.05 or smaller. So on the right, I have the ranks. We saw this before when we looked at the median, the MAD, and Spearman correlation. So when we look at the ranks, those two values no longer look so big. And when we compute the Wilcoxon test on this data, we actually get a p-value of 0.22. So what is it that we do? Let's just explain it very quickly. It's quite simple. What we do is for each number here, we compute how many values are smaller than that number on the other side. Right? So for these guys over here, they're all 0. Then we have one number smaller, 2, 4, 5, etc., all the way up to here. So if, in fact, this group has smaller ranks, most of these ranks should be smaller than half of 25. So when we sum them up, if we sum them up, we get 248. If we divide that by 25, the total number of ranks, then we should get a number under the null that's about 12.5. And that's close to what we get here. Now, you can perform some mathematics to figure out what the chances of seeing a number as big or as small as 248 to get a p-value. Those computations are a little bit technical. We're not going to describe them here. But we will explain how you can construct a z-score for this sum of rank statistic. Here's how you construct the z-score. So you take that sum, which is usually denoted with a u, and you divide it by the size of that group, n1. So this is basically the average rank. Under the null, where the ranks are the same on both sides, that should be roughly about n2, the size of the other list, divided by 2. It should be around the middle. The trickier part is computing a standard error for this difference. And with a little bit of mathematics, you can show that this is the standard error of this difference. So we can also use the central limit theorem to motivate that u is going to be asymptotically normally distributed. It's going to be approximated by a normal distribution. So this z-score, when n1 and n2 are large enough, is going to follow a normal distribution with mean 0 and variance 1 when the null hypothesis is true. And we can use that to obtain p-values.